Good.
Okay, great. Okay, so I'm Stuart Bale. Our experiment is called the Lunar Surface Electromagnetics Experiment, LuSEE, and we were selected under the LSITP program in last July. I'll give you a summary at the beginning and a summary at the end. First, basically LuSEE is an instrument, a suite of sensors to measure and characterize the electric and magnetic field environment on the lunar surface, and that includes DC electric fields, DC magnetic fields, plasma waves, and low-frequency radio astronomy as well. The instrument is built up from flight spare components from our instrument on Parker Solar Probe, the Fields instrument on Parker Solar Probe, with some, essentially the main electronics come from the Fields instrument on Parker Solar Probe and the flux gate and search coil magnetometers.
The meeting.
Sorry?
Yes, I saw it. I said yes.
Sorry, is there a question? The sensors, the electric sensors come from stereo waves and Van Allen probes. We're kind of going back and forth between a Van Allen probe sensor and a Maven sensor, so I'll come back to that. The team is the same team that built these instruments, and so we're coherent, we're working together daily, and we're under contract, and we've started work on assembling the hardware. So the science objectives are a little bit exploratory. We want to look at and characterize the lunar ionosphere, and we'll do that using plasma waves, quasi-thermal noise emission, which tells us about electron temperature and density. We can do that with a simple set of antennas. We want to look at geospace surface interactions, so that includes electron interactions with the surface of the moon, the magnetic fields, the lunar surface potential. We want to characterize the potential itself, the electrostatic potential, which flows into dust transport, and we will do some pathfinding low-frequency radio astronomy. So here I just have some images of the lunar ionosphere from some work by Jasper Hallekas with Themis or Artemis mission. On the right-hand side, you see, I don't know if you can see my cursor, but this spectrum in the second panel down is the radio spectrum from some tens of kilohertz up to about 20 megahertz using our instrument on Solar Probe. And those modulations that you see there are the galaxy. As the spacecraft rolls around, we're seeing the galactic synchrotron electron spectrum, or the synchrotron spectrum from the galactic cosmic ray electrons. The stuff you see in the third panel down and fourth panel down is Jovian radio emission on the far right side. That's circularly polarized emission from EO modulated plasma. So we'll be sensitive down to the level of the galaxy. We'll see planetary radio emission, we'll see terrestrial radio emission, and we'll see the galaxy and the sun. The panel on the left shows is a simulation by Andrew Poppy, who's one of our team members of surface potentials. Of course, we're interested generally in the surface potential, especially as we transition to the limb, where we should see some electric field effects that are, as we heard in one of the earlier talks, potentially responsible for dust transport or a factor in dust transport. And then we can potentially see actually dust impacts themselves. So at least when you put a spacecraft like this or a sensor like this on a system in orbit and a dust particle hits the spacecraft, you can actually count those dust particles. They produce little voltage blips on the spacecraft, sort of millisecond, large fractions of a volt potential modulations to the spacecraft that we can count and measure, and we're doing that with Solar Probe. We've done it with stereo, with wind, Cassini, etc. So here on the surface of the moon, this is a little more sketchy because the dust velocities, it's a strong function of the speed of the dust particle, and the dust velocities are much lower, but we'll try. Okay, so what do we actually measure? We measure the vector magnetic field, the DC magnetic field, with a Goddard flux gate magnetometer. We'll measure the AC magnetic field potentially up to megahertz frequencies with the search coil magnetometer, and we'll measure. We have three sensors that will measure single-ended and differential voltages. So these will be something we can turn into electric field measurements. They're current biased sensors, so they're not just floating voltage sensors. They're current biased sensors, so they can actually we drive them close to the local plasma potential, and we'll measure a true electric field from them. And then again, as I said, we'll measure the quasi-thermal noise spectrum, which gets us the electron density and temperature to pretty high fidelity, and the radio emission spectrum. So the block diagram is like this. You don't have to look at all the stuff on the left, but basically it's a stack of electronics on the bottom part, and that stack of electronics is essentially all Parker Solar Probe flight spare hardware. We've got either fully assembled boards or parts kits for almost all of it. There are a few things we're sending out to have fabricated, but it's, we could sort of start putting it together in the next few months. And I'll show you the sensors in the next few slides, but we have 3 voltage sensors and 2 magnetometers that block into all this stuff. That's a picture of the main electronics package on the Parker Solar Probe spacecraft. So it's a kind of bread box size stack of stuff. We have 2 fewer boards than is on Solar Probe. As I said, some of the boards are complete, some are kitted, some are needs a little bit of fabrication for and things. Okay, that's what we want to look like on an orbit, on a lander. So that's a mock-up of a lander. We want to deploy 2 sensors. So I don't know, again, if you can see my cursor, there are 2 stereo waves antennas that will deploy out to form a dipole. And we'll deploy them out at an angle so that they sag a little bit in lunar gravity to be at their tips kind of horizontal. Okay, so we'd like them to function as a dipole for radio measurements and to function as a ground plane for a DC electric field measurement. Then the thing that's popping up here is, okay, here I say Maven, but we're kind of leaning towards our RBSP, our Van Allen probes flight spare, which is almost the same thing. And so we'll deploy one stator boom upward. These are what are called stasers. I'll show pictures of them on the next slide. We'll deploy this one upward, and that'll have a voltage. That will have a voltage sensor at the top, and we can difference that voltage with the voltage of the ground plane. Is there a question or just an open mic? Okay, then we have 2 magnetometers, the Fluxgate magnetometer and a surgical magnetometer that will deploy out on composite carbon composite booms. This is a picture of the stereo waves flight spare. We have 2 of these in the lab at Berkeley. They're flight spare units. They're fully, we'll deploy them, clean them up, etc. But they should be ready to go. They are 6-meter beryllium copper stator units with tie-night pin puller things. So there's no motor to deploy. They're basically a spring. You pull the pin and they pop out to the full 6-meter length. They pull a wire out in the center that rate limits the thing so we can control how quickly it deploys. These are ready to go. So this is a picture of the Maven axial boom, which is similar to the one for RBSP. So this is basically a similar thing. It deploys up straight away from the spacecraft, and it will have a cable, a harness running in the center, and a sensor at the tip of it. Similar kind of thing as the stereo sensor. So we've flown hundreds of these stasers on rockets and on spacecraft, and they're very reliable. They don't need a motor to deploy, and they're very robust. Okay, the booms for the magnetometers will be flight spares from the Themis mission, which some of you probably know as Artemis, the first Artemis, or the latest Artemis. So the Fluxgate mag boom is a 2-meter 2-segment boom. It's got a hinge at the base, a hinge at the elbow. It'll pack up. You see the CAD drawing here. We can pack it up like that on a spacecraft. This is on the shelf at SSL at Berkeley, and the search coil boom will be a 1-meter similar boom. Sorry, it says elbow hinge. There's no elbow hinge. It's just a single hinge at the base. And that picture are the 2 booms on an actual Themis spacecraft in the lab at Berkeley. And that's Greg Dalton, who is one of the engineers who will work on this with us. Our resources are kind of in the envelope of the AO. We have on the order of 15 kilograms or so of hardware. We have on the order of 15 watts, although that can be duty cycled. We can turn things on and off if we want to bring that down. We can produce a lot of data. We can produce megabits per second of data. On Solar Probe, we bring down something like 50 kilobits per second of data. We can bring down anything that's available. And finally, the team. So the team is basically the same team that did Solar Probe fields, and much of the team that did stereo waves and RBSP as well. So we're leading it at Berkeley. We've got the same subsystem leads as we had on Solar Probe. And we've got a science team that includes some people who know about radio astronomy and about lunar surface and lunar plasma things. And then I'm back to the summary slide again. So again, we're going to measure the electric and magnetic field environment of the lunar surface, plasma waves, radio astronomy. So this will tell us about geospace interactions with the surface. It'll tell us about dust transport. It'll tell us about, it'll be a pathfinder for a good radio instrument on the surface. We're made up of flight spare hardware. We've got almost all this stuff on the bench. You know, we can start putting it together. It's the same team who did it last time, and we're starting to work now. And that's it.
Great, thank you. I think we've got time for maybe one question. If there is one question. Okay, great. If there's no questions, we'll transition to the next speaker. Thanks very much.
Great.